Welcome. The topic we'll be discussing in this lecture is paging. So paging basically it allows a process to occupy locations in a memory in a non-contiguous way. Paging allows process to occupy locations in memory in a non-contiguous way. And also paging avoids the problem of external fragmentation, and also it avoids the problem of varying sized memory chunks. That is, memories of different chunks will not get wasted because of paging. Okay. So basically paging, what paging does in the sense, it divides the physical memory into several fixed size blocks, and these fixed size blocks are called as frames. The physical memory is divided into several fixed size blocks, and these fixed size blocks are called as frames. The size of a frame will be typically in the power of 2. The frame size can be somewhere between 512 bytes and 16 megabytes. But every frame should be of same size. You cannot have different frames of different size. No. The memory is divided into fixed size blocks. These fixed size blocks are called as frames. The frame size can vary between this and this, 512 bytes to 16 megabytes. That depends on your memory capacity and all other things. Okay. Similarly, paging divides the logical memory also into blocks of same size. The physical memory is divided into fixed size blocks called frames. Similarly, logical memory is also divided into fixed size, where each size of the block will be equal to the same as that of the frame size. Okay. Whereas each block in a logical memory will be called as pages. Okay. Each block of physical memory is called as frames, and each block of logical memory will be called as pages. So if you want to execute a program which contains n pages, then the operating system should identify n free frames in the physical memory to load that particular program. And these n free frames need not be contiguous. These n free frames need not be contiguous. Okay, it can be anywhere in the memory. Okay, so assume that in the logical memory you have n pages. Say you have n pages. So logical memory is a programmer's view. So generally logical memory will be treated as contiguous memory. So you have n pages 0 to n minus 1. Now you want to load these into the physical memory. So in the physical memory, there may be some free frames in between, there may be some occupied frames. Okay, it can be of any order, right? So these n free frames need not be contiguous in the physical memory. It may occupy different location. Zeroth page may come here to frame 0, and first page may come here. Okay, it may be frame 10. In physical memory we call it as each blocks, we call it as frame, whereas in logical memory we call it as pages. Okay, so this is L represents logical memory and P represents physical memory, and the next page may come to the frame number, say 7. Like these different pages may take different frames, and it need not be contiguous. Operating system will do that allocation. Okay. So basically pages, uh, uh, the memory, the process occupies non-contiguous locations with paging, right? And there will be something called as page table, which will convert the logical address to physical address. So the page table is the one which converts the logical address to physical address. Okay. So paging, it solves the problem of external fragmentation, but it doesn't solve the problem of internal fragmentation. With paging also we may have internal fragmentation. Okay, fine. So as we have already discussed, so there will be a logical address, and this logical address will be converted to physical address through page table. So what are the components of this logical address? So it is somewhat similar to the segment table. So the logical address, it contains two things. One is it contains a page number. The logical address contains two things. One is it contains a page number. Okay. So let me call it as PG number. And then it contains a offset. And then it contains an offset. So these are the two things a logical address contains. Okay. And here what will happen in the sense, the page number will refer to, will indexed, is used as an index of the page table. Okay. The page number will be acting as an index to the page table. So you will have a page table. So in the page table, uh, here the page table will have only one column, not two columns. In the segment table contains two columns, but the page table has only one column. Okay. And this page table, what it contains in the sense, it contains the starting address of a particular page. Okay. So like say there are starting address of a particular frame in the physical memory. Okay. The pages are nothing but what do you call, pages are nothing but in the logical memory, whereas frames are in the physical memory. So these are the so page number 0, what will be its starting address? Starting address of the respective frame. Okay. Page number 1, what will be the starting address of the respective frame? Page number 2, what will be the starting address of the respective frame? Page number 3, what will be the starting address of the respective frame? Like that, for all the pages, the respective starting address of the corresponding frame will be available in the page table. Okay. So this value will be fetched and it will be directly added with the offset. Okay. By adding it with the offset, the physical address will be identified. Okay. So this is how it works at the top level, but there are some internal things which we will discuss in detail. Okay. So basically, a logical address contains two things. One is a page number, the other one is an offset. So the page number is used as an index to the page table, and then which contains the base address of the each page in the physical memory. Okay. So in the physical memory, actually we don't use the term page; it is frame. Okay. And then that particular base address will be added with the offset to produce the actual physical address, right? So this is how the logical address will be converted to physical address. Okay. And uh, this logical address will have this many bits. How many bits it will have? In the sense, it will have m minus n plus n bits. The logical address will have m minus n plus n bits. So what is m and what is n here? So m represents, if the logical address contains 2 to the power m locations, if the logical address contains 2 to the power m locations, that is from 0th location to 2 to the power m minus 1 location. Okay. Assume the logical memory contains 2 to the power m locations, that is 0 to 2 to the power m minus 1 location. Okay. And so logical address contains m locations means, sorry, 2 to the power m locations mean it contains 2 to the power m pages. So it means each location is nothing but a page. It contains m 2 to the power m pages. Okay. So if you take one page, then we say that this one page contains 2 to the power n locations. This one page contains 2 to the power n locations. That is, each page will have 0 to 2 to the power n minus 1 location. Each page will have 0 to 2 to the power n minus 1 location. Okay. So that is how this m and n were derived. Okay. So m represents, so m is nothing but the logical address space contains 2 to the power m locations, and that is 2 to the power m pages, and each page contains 2 to the power n locations. Okay. Then the logical address will have m minus n plus n bits. Okay. Where first m minus n bits will refer to the page number. The first m minus n bits will refer to the page number, and the next n bits will refer to the offset. First m minus n bits will refer to the page number, and the higher order m minus n bits will refer to the page number, and the lower order n bits will refer to the offset. Okay, I hope it is clear. So here what is m and what is n in the sense, for a given logical address space, 2 to the power m locations, okay, and the page size is 2 to the power n. So if the logical address space is 2 to the power m locations and each page size is 2 to the power n locations, then the logical address which is generated by the CPU can be represented by using m minus n plus n bits, where the higher order m minus n bits will refer to the page number and the lower order n bits will refer to the offset. Okay. As of now, you remember this as a formula. We will discuss this with examples, then things will get clear. Okay. So this is how the paging hardware works at a top level. Okay. So the CPU creates a logical address which contains page number and the offset, and there is something called as page table. So the page table, the the page number of the logical address will index to the page table. So page table contains several locations, 0, 1, 2. So basically this 0, 1, 2 refers to the various pages. Okay. So so how many pages will be there? As of the previous slide, there will be 2 to the power m minus 1 pages. So totally 2 to the power m pages, starting from 0 to 2 to the power m minus 1 page. Okay. Maybe this particular P, it may refer to some kth page. It may refers to the kth page. So kth page, what is the actual frame address for page K? What is the actual starting address of that particular frame? That will be available here. That will be taken and that will be added with the offset to create the actual physical address. Okay, that will be the page number will act as an index to the page table, and the respective entry in the page table will refer to the physical address, will refer to the starting physical address of that particular frame, and that will be added with the offset D to create the physical address. Okay, so this is how at a logical address is converted to physical address at a top level. Okay, still we have not discussed in detail, we'll discuss. Okay, so this particular slide shows how the page numbers are mapped to frame numbers, how the page numbers are mapped to frame numbers. Let us assume the logical memory contains only 4 pages, page 0, page 1, page 2 and page 3. Then your page table looks like this. Okay, so there is a entry for page 0, there is a entry for page 1, there is a entry for page 2 and there is a entry for page 3. So what does this entry represents? It means that page 0 refers to frame 1 of physical memory. Okay, and page 1 refers to frame 4 of the physical memory, and page 2 refers to frame 3 of the physical memory. Okay, and page 3 refers to frame 7 of the physical memory. Okay, this is how the pages are mapped to frame numbers. Okay, who will do this mapping? Operating system will do. So when these pages arrive, when the logical memory, so this all these pages corresponds to some particular process, say a particular process pi. So the process pi contains this many pages. Now the operating system should execute this process, so it means it should load all these pages to the memory. So then operating system checks what are the free frames and in some order it will allocate. Okay, so it need not allocate in a contiguous way. So operating system decides to provide uh, frame 1 for page 0 and frame 3 for page 2 and frame 4 for page 1 and frame 7 for page 3. So it allots and accordingly it fills up the page table. So 0th page will go to frame 1, first page will go to frame 4, second page will go to frame 3, third page will go to frame 7. Okay. So this is how the page numbers are mapped with the respective frame numbers. Fine. So still we have to discuss like how the mapping was done at address level. So this particular diagram, it clearly shows how the mapping is done at address level. So as we have already discussed, the logical address will have m minus n plus n bits. Okay. So out of that m minus n plus n bits, the higher order m minus n bits will refer to the page number, okay, which will index to a page table, and the lower order n bits will refer to the offset. Okay. So let us take an example where m is equal to 4 and n is equal to 2. So m is equal to 4 means what? 2 to the power m. There are 2 to the power m locations in the logical address. So in our case, m is 4. It means there are 2 to the power 4 locations in the logical address. So 2 to the power 4 is nothing but what? 2 to the power 4 is nothing but 16. So the logical address contains 16 locations. So see this particular table, the logical address contains 16 locations, 0 to 15. So there are 16 locations. Okay. And n is equal to 2 means what? 2 power n is equal to, in our case, n is 2. So 2 power 2, which is nothing but 4. So n 2 to the power n represents the size of the each page. So each page occupies 4 locations. So you can see each page occupies 4 locations. 0, 1, 2, 3. Okay, each page occupies 4 locations. Similarly, next page occupies 4. 0, 1, 2, 3. So like this, every page occupies 4 locations. Okay. So this is page 0, this is page 1, this is page 2, and this is page 3. Okay. This m also represents number of pages. Okay. There are how many pages? 4 pages. 0 to 3 pages. Okay. Right. So there are 4 pages, and each page there are 4 pages, totally 16 locations, 2 to the power 4, and each page occupies 4 locations. Okay, fine. and and this is how these pages were and this is how these pages were mapped to the frame. Page 0 goes to frame 5. Okay, page 0, this is page 0, this is page 1, this is page 2, and this is page 3. And as per the page table, so this operating system allocates page 0 is allocated to frame 5. So page 0 is allocated to frame 5. Okay. Now what is frame 5? Okay, so you can, so it's here, this is the physical memory. So you can number these frames also: 0, 1, 2, 3, 4, okay, 5, 6, 7. Okay, physical memory can have any number of frames, but currently we are showing only 7 frames. So page 0 goes to 5th frame. Page 0 goes to 5th frame. Okay, that as per the page table. And page 1 goes to 6th frame. Page 1 goes to 6th frame. Okay, and page 2 goes to 1st frame. Page 2 goes to 1st frame, and page 3 goes to 2nd frame. Page 3 goes to 2nd frame. Like this it is allocated. Okay, so this is how the page is mapped to the particular frame. Okay, there is also another way to do this mapping. So here you see page 0 is mapped to frame 5. So how to identify the exact address of frame 5? In the sense, this 5 you just take and multiply with 2 to the power n. So in our case, n is 2. So 2 to the power n is 4, because each frame or each page occupies 4 locations. So 5 into 4 is what? 5 into 4 is 20. Okay, 5 into 4 is 20. So it means that page 0 starting address will be, the page 0's starting address in the physical address will be 20th location. Okay, so you can see the starting address, page 0. Okay, similarly page 1 is mapped to frame 6. So how to identify frame 6 starting address? 6 into 4, that is 24. Okay, similarly page 2, it is mapped to frame 1. So 1 into 4 is 4, so that is its starting address. Similarly page 3, it is mapped to frame 2. So 2 into 4, 8, that is its starting address. Okay, so this is how, this is the, like this also you can map. Okay, just multiply the particular frame number with 2 to the power n, right? Okay, fine. Now let us see how to map address wise. How address wise mapping is done. Okay, that is with respect to a particular address, how a logical address can be converted to a physical address. Okay, so let us assume address 0. So address 0 of logical address, how it will be converted to physical address. So first you recall the logical address will have what will be the size of the logical address. The logical address will be divided into two parts. The higher order bits will refer to the page number and the lower order bit will refer to the offset. And the size of the higher order bits will be m minus n, okay, and the size of the lower order bits will be n, okay. So in our case, what is m4, what is n2? So the size of the higher order bits will be 4 minus 2, okay, and the size of the lower order bits will be 2, okay. So 4 minus 2 is 2, 2. So totally there should be 4 bits. Totally there should be 4 bits in the logical address for this particular example with m is equal to 4 and n is equal to 2. Okay. So first let us convert this logical address to 4 bits. So our logical address is 0, convert it to 4 bits, that is represented in binary. So 0, 0, 0, 0, okay. So 4 zeros. So basically we got 4 zeros. So here first m minus n bits, that is first 2 bits refer to the page number and the next 2 bits refer to the offset. Okay, so first 2 bits is 0, 0, convert it to decimal, it is 0. So it means that it refers to the page 0. What is page 0? 5. Page 0 refers to frame 5. Convert this into the equivalent address. So that is 5 into 4 is 20. It refers to the address 20. Okay. So page 0, it refers to the frame number 5. And if you multiply that with 2 to the power n, what you get is 20. The starting address is 20. Okay. Now this 20 should be added with the offset. So what is our offset? 0, 0. Convert this to decimal, again it is 0. So 20 plus 0. So 20 plus 0 is nothing but 20. So 20 plus 0 is nothing but 20. So the logical address 0 refers to the physical address 20. Logical address 0 refers to the physical address 20. Okay. So that we got this page number is 0, offset is 0 and the physical address is 20. Okay, like this you can calculate the other things also. So let me calculate one or two more. Rest of the things you can work it out. So say for example page number, yeah, logical address 3. Logical address 3, how will you represent in binary? So logical address 3 is nothing but 0, 0, 1, 1. Okay, again first 2 bits refers to the page number, next 2 bits refers to offset. So first 2 bits is 0, so page number is 0. Page number 0 refers to which frame? 5th frame. So 5th frame, convert the 5th frame, how to get the 5th frame's address? Multiply by uh, 2 to the power n, that is 5 into 4 is 20. Okay, so the base address we got, that is 20, and now that should be added with the offset. So in this case, what is offset? 1, 1, convert to decimal, 1, 1 is 3. So 20 plus 3 is 23. 20 plus 3 is 23. So the logical address 3 refers to the physical address 23. So logical address 3, what we have? D. And the physical address 23, what we have? D. This is 20, this is 21, this is 22, so this is 23, D. Is it clear? So like this you can do for other things also, right? Say let us take this 15. Let us take this 15. Okay, 15, if you convert to binary, 1, 1, 1, 1. Okay, the higher order 2 bits refers to the m minus n bits. Here m is 4, n is 2, so for 2 bits. Okay, so it refers to the page number. So 1, 1, if you convert to binary, it is 3. Offset is also 3. Okay, so this represents the page number. Page number 3 mapped to frame number 2. Page number 3 is mapped to frame number 2. So if you multiply 2 into 2 to the power n, that is 4, which is 8, okay. Add this 8 with, the offset is 3. So when you add this 8 plus 3, uh, what you get is 11. So the logical address 15 is converted to physical address 11. So logical address 15 you have p. At physical address 11, this is 8, 9, 10, 11, that is also p. Okay. So like this you can calculate the missing things, right? So this is how the concept of paging works at address level. Okay, I think it's clear. So I want you to fill up these missing values. Okay, fine. Okay, so now already we discussed that paging will create a problem called internal fragmentation. Let us discuss that with an example. Okay, so let us assume that the page size is 2048 bits. Okay, let us assume that the page size is 2048 bits. That is, in the previous example, we have discussed page sizes only 4 bytes. Okay, but here the page size is 2048 bytes, not bits, 2048 bytes. That is, you are dividing the memory into the logical memory into several pages. Okay, where several fixed size pages where each page occupies 2048 bytes. Okay, the size of a one page is 2048 bytes. Okay, right? So if page is page is connected with logical memory, so the physical memory also, there will be equivalent frames in the physical memory. Each frame will occupy 2048 bytes. Okay, the physical memory, each frame will occupy 2048 bytes. Okay, now assume that there is a process. And the size of the process is 72,766 bytes. There is a process, the size of the process is 72,766 bytes. Okay, this should be loaded into memory. Okay, so how many pages it requires? So you just divide 72,766 by 2048. So if you divide that, what we are getting in the sense, when you divide this by this, process size by page size, what we are getting is around 35.53. 35.53. Okay, so it means that it needs 35 pages. It needs 35 pages. To accommodate this particular process, we need to allocate 35 pages plus 1086 bytes, plus 1086 bytes. But how will we allocate this 1086 bytes? Our memory is divided into fixed size pages. Okay, each page occupies 2048 byte. You cannot allocate 1086 byte alone. For that 1086 byte also you have to give one page. Okay, so one page will be given. So how much memory will be wasted? Out of this 2048 bytes, the last page, out 35 pages it needs. Okay, 35 pages plus 1086 byte. For this 1086 byte, we are going to allocate one more page, that is 36th page. So this 36th page is going to occupy only 1086 bytes out of 2048 bytes. So 962 byte is wasted. So this 962 bytes which is getting wasted is called as internal fragmentation. Okay, so this wastage is called as internal fragmentation. So in this example, 962 bytes is wasted. Okay, in some other example, some more bytes may be wasted. So worst case, how many bytes can be wasted? In worst case, like this, how many bytes can be wasted?